So today we'll be taking a look at the continuous uniform distribution, and I'll also show you how you can use it to simulate other more complex distributions. So we say a continuous random variable x is uniformly distributed on the closed interval AB if it has the following probability density function, where f of x equals the constant 1 over b minus a for x within that closed interval and 0 everywhere else. It should also be noted that a and b are the lower and upper bounds of the distribution, so you can't have b less than a or some weird thing like that. And if you think about this related to our discrete uniform case, this makes a lot of sense, right? When you're modeling equally likely outcomes, your PDF intuitively has to be constant over the range of possible outcomes and 0 everywhere else. So if you want to make a verbal argument, or if you just want to integrate over the PDF to try to find the CDF, do that now. Pause the video. I'll let you take a second to do that, and I'll show you the CDF right now. So this is the CDF of our continuous uniform distribution. And before I show you how to find this with integration, just take a look at the slope of our 3 different cases, right? Outside of our range, it's 0, but within our range, it's 1 over b minus a. So think about how that relates to our PDF. So this is how you can prove this pretty simply. And I'll just walk you through each case a bit. I'm not going to read these exactly. But for x less than a, right, when I say no values below a are in the distribution, I mean that when x is less than a, all of those values below x, right, they're also less than a. So by our PDF, we know they have likelihood 0 of happening. So of course, our CDF has to be equal to 0 there. Now for the second case, all I'm going to show you, as this is a pretty standard integral, is just don't forget your dt, right? This is a function of x. Be careful with that. And lastly here, when I say the entire distribution has been covered, what I mean by that is that we've seen all of the non-zero values in the distribution. So by the core properties of probability, we know that our CDF has to equal 1. And in the next slide, I'll show you how to derive expectation. Remember, use your law of the unconscious statistician. Give this a shot. Pause the video here. So you'll see here, right, that our expectation for the continuous uniform case is pretty straightforward, actually. All I'm doing here, right, in the first step is I'm just restating our law of the unconscious statistician. And here, I'm just restating our PDF. So none of this is new, right? You can, if you want to ignore it, you can. None of this is new. And this is our integral. And you'll also see that our integral is actually pretty straightforward. The trickiest part is completing the square, how miserable that is with all the algebraic manipulations or whatever. But our final result is what I want to draw attention to here. If you think about what our PDF looks like, right, with our straight line, it kind of makes sense that the expectation, which is really the mean, so the average, is right down the middle. Think about, your class average or whatever, and what average means, right? What mean means. And you'll see that you could have probably derived this without integrating it. And next I'll show you the variance, and that unfortunately is a bit trickier to find without integration. But you can do the integration. The integration is equally straightforward. So give that a shot. Pause the video. Right? Our variance is a bit weird, but there's nothing really tricky here. This first part, all I'm doing is restating the definition of variance. Here we have another one of these x to the n integrals, right? This is nothing new. You just did one of these on the last slide, except this time it's x squared instead of x, but it's identical, right? And this last step, right, despite, again, we have this weird algebra, whatever, but all you're doing is plugging in this result here, and this is our e to the x. Right? I'm sorry about the handwriting there, but that's what that is. So yeah, all I want to draw your attention to here is, how you find variance for continuous distribution. But really, once you see how to do it, all of the mechanics here, this stuff should be pretty straightforward. So think about the definition of our moment generating function, right? Which is the expectation of e to the tx, right? And give that a shot right now. Pause the video, do what you need to do. So while at first glance, the MGF might be a bit intimidating for this uniform case. When you look a bit closer, you'll find that it's pretty straightforward actually, right? Notice that these first two steps, I'm just restating definitions, right? This is the definition of the MGF for all distributions, and this is just our PDF. I'm just restating that. So like we did in the last slides, right? You can ignore these first two steps and just focus on this step right here, right? Here you'll see that our MGF, right? It depends on t. You know that. This is just the nature of our MGF. But by definition, right, our integral, it's dx. We don't care about t here. So you can't be intimidated by this e to the tx. Like I get that, you know, you might be intimidated or whatever. Just treat it like another integer. Treat it like e to the kx. And then after that, you know, this is trivial. Bring your k down, you're done. And I will draw your attention to this note. It really should be emphasized that this MGF works for any t except t0, right? Because here, if t was 0, we'd have 0 over 0. And you don't want to deal with this indeterminate form right now. Just remember that for the moment generating function, right? When t is 0, we need to have this, right? We need to have mx0 equals 1. So next I'm going to show you the most important part about the uniform distribution. And yeah, we'll just jump right into that. So feel free to pause the video, you know, rewind, go over this as many times as you need, and really make sure you understand how to do this part, because I can guarantee you will be tested on this. So first, you know, we'll read through the intuition a bit. If you generate a random number u from our u 0 to 1 and plug it into the inverse CDF of a distribution, you will get a random variable following the distribution. So I know it seems like a crazy result, but just think about the definition of all CDFs, right? And you'll find that they're uniformly distributed over the interval 0 to 1. So once you've kind of understood that, you'll see that to simulate, you know, in this case, we're doing x follows, you know, exponential of lambda. You can use this thing called the inverse transform method. Now, really pay attention here. All you need to do at the end of the day is set f of x equal to u, solve for x, and then, you know, rewrite it as big X and big U. I know it seems like it's a bit of an oversimplification, like in terms of what's going on, but really at the end of the day, that's all you need to do. So, you know, this result, this end part right here, you're going to prove that in the next slide in the exercises. So yeah, pause here, understand that, and then I'll let you get to the exercises. So here I've given, you know, a handful of practice problems, and I just want to say thank you for listening. I really encourage doing these. You know, feel free to ask any questions. You know, if you want solutions, ask in the comments. If I messed up at any point, if you don't understand anything, you know, please let me know. I really do care. Thanks again.